Let's dive into two examples. So I want to be able to take one example where we have a normal vector and then we have a point, and we're going to assume that that point is on a plane, and we're trying to find the actual standard equation or the scalar equation of the plane ax plus by plus c z plus d is equal to 0. So that's one item that we're going to try to do. Now I'm going to do this through the dot product just to show you where this standard equation actually comes from and how the dot product is interlaced with it. Now we don't technically need the dot product to be able to find this equation, and I'll show you why. But having an understanding how the dot product works with the scalar equation is actually pretty useful, and most likely if you're going to be studying vectors at some point, okay, maybe in grade 12 or somewhere else, you're going to be running into this, and maybe your teachers are going to be asking you about this kind of equation and how to find it through the dot product. The second example that I'm going to be jumping into is actually going to be from given 3 points, and we're assuming that those 3 points are on a plane that we're trying to find, again, the standard equation of the plane. And how do we do that? And I want to be able to tie in the cross product, which is going to find our normal. And then I'm going to tie in the dot product from the first example so that we can find our equation of the plane. So let's jump into these two examples. So in the first example, what we have, you can imagine that we have some kind of a plane. Now on this plane, so we can assume that we have that point P1. Now I don't know exactly how that plane looks like, but let's assume that we have a point P1 right there. We have a normal, and again, so this is not going to be the exact normal right here, but in any case, I'm going to draw it. Okay, so I'm going to draw it up, although it's clearly not up because it's 3, 2, 4, so that's the vector. Now we know that this is perpendicular to the plane, and we want to be able to find this particular equation. So this is what we want to be able to find. So one way to be able to do this is to simply take in and recall that the normal vector right there actually gives us the A, B, and C values that we have. So I have actually discussed that. I can put that up above there. And if you know that, then finding the actual equation is not very difficult, and we don't need the dot product. So what we would do is we would simply substitute. So we would have 3x plus 2y plus 4z. Now we don't know what that d is, at least we don't know what that d is yet. Now we can take our point and then we can substitute it into our equation. And if we would do that, we would get, so this is going to be 3, so times 1, 2 times 1, and 4 times negative 1, so that's negative 4, plus d is equal to 0. We can add it all up, so that's 5, that's 1, bring it on the other side, so we're going to get d is equal to negative 1. And so there we go. So we have our, so instead of this being d, we can substitute in here, so it's going to be negative 1, and that's our equation. And you might say, okay, so great. Why do I need the dot product? You don't need the dot product per se to be able to find this equation. However, it is actually worth your time to try to understand where this equation comes from and why does this work. And actually, how does the normal relate back to that A, B, and C? Well, where that all relates back in is to this fact. So if this is our normal, and this could be any normal that we would have. So let's say that this is our normal, I'm going to call this A, B, and C, although we have it as 3, 2, 4. And now if you know, and if you want to be able to find this equation of this plane, you can literally take any point on the plane. So it doesn't have to be that P1. It can be any other point because we already know P1. So if you take a point and let's say, I don't know, maybe it's a point somewhere over here. Now, what we know by vectors, we know that we can create, okay, this vector right there. Let's say that this is point P. Now, since this is an arbitrary point, I'm going to call this X, Y, and Z. So those are going to be any point that I would like to have, so long as it's on the plane. And now, what do we know? Well, we know the following. We know that if we wanted to take the dot product, so now what I'm going to do is I'm going to take the dot product between my normal and the dot product between this particular vector. So this vector that I drew right there. So that vector I can call, so this is, let's say, the point P, P1. Okay, so this is my vector, which goes from P to P1 or P1 to P. It doesn't matter the direction, to be honest with you. We know that because the normal is perpendicular to the plane, we know that the dot product between these two vectors, this n and this, where P is any point x, y, z on the plane, is going to be equal to 0, because the dot product when two vectors are at 90 degrees is 0, because if you recall, the dot product has the cos between the two vectors, and cos of 90 is 0. So if we have this, then we can very nicely actually construct our equation, our standard equation. So if my normal, let's say, was indeed, some A, some B, some C, that I knew what it was, and I would be dotting it. Now, notice what's going to happen here. Okay, so the P and P1, so it's really the subtraction of those two. So what I would have is, I would have my actual values. Now I'm going to shift this a little bit just so that I have space. So this P and P1, if I would do that, and maybe I'll do that here on the side. So it would be X, Y, Z, right? Minus, now I guess I can remove and create this as now a vector, minus the P1. So now in our case, we know exactly what this is, but let's say that this is, P1X, this is P1Y, and then this is P1Z. Now if I subtract those, what I will get is I'm going to get the components of X minus P1X. That's going to be my component of X. Then I'm going to get Y minus P1Y. And then I'm going to get Z minus P1Z. And this is the actual dot product now in between. And if I distribute this across, so notice that if I take the A, right, because I'm going to be working with the dot product all the way through, right, so 1 by 1 by 1, then what I will have is, I'm going to have a nice equation where it's going to be A multiplied by X minus the P1X plus my B, which is going to be Y minus, this is going to be P1Y, and then plus my C, and then this C is going to be multiplied by Z minus P1Z, and this whole thing is supposed to be equal to 0. Now, if I distribute this, right, inside of here, so I can distribute this across here, I can distribute this across right here, and then this across right there. And if I distribute all of that, I know I'm going to get A times X plus B times Y plus C times Z. And then that point P1 times A, B, and C, that's going to actually create my D, because it's going to be just an arithmetic multiplications and additions between all the different numbers that I have. Now you might say, well, this seems very complicated. I like doing this, it's much faster. And I agree with you. I also like doing that. I don't necessarily like doing the dot product, but I wanted to introduce this dot product between the two vectors, the normal and any point, and one point that is given to you, because I know that teachers do utilize it. And to be honest with you, that's kind of where the scalar equation comes from. Because notice scalar, well, the dot product does give us a scalar back. And now for any x that is on the plane, we actually now have an equation. And that equation is going to be our ax plus by plus c z plus d is equal to 0. That actually comes from this dot product. So although you might like this, and then the knowledge, okay, of your normal, which is great, but this is actually where it comes from. It comes from this dot product. So if I were to do this with our example that we actually just have done, then what we're going to get is we're going to get the following. So here's my normal. So my normal was 3, 2, 4. I'm going to dot it with, now this is going to be x, right? And I'm going to have to take that point. Now that point is, so it's going to be x minus 1, y minus 1, and z minus minus, so it's going to be plus 1, is equal to 0. So now notice what's going to happen. This is going to be just now 1 by 1. So I'm going to do this first. So it's going to give me 3x minus 3. I'm going to now do the other one, so second. So it's going to be 2. So that's going to be 2y minus 2. And then finally the 4, so plus the 4z plus 4 is equal to 0. So now 3x, 2y, and 4z, so that is nothing different than what we had done. And now I can add all of these together. So notice negative 3, negative 2, and then 4, so that's going to be actually minus 1 is equal to 0. And it does indeed give us the same equation that we had right here. So if you choose to do it by the dot product in this way, or as you know, the normal is just your a, b, c, and then you can substitute your point in to find your d, it does not matter which one you do. So now you have the tools and you have an understanding how the dot product actually has tied in to this standard form or scalar form of an equation, of an actual plane. So that's what you have there. Now, in this second example, so what we have is we don't have a normal, right? We have 3 points, okay? And if you recall, so you do need a minimum of 3 points, and you're assuming that they're not collinear, so they're non-collinear points. You don't want them in a line. We do need them to be non-collinear so that they actually kind of create a triangle so we can get a plane out of it. So if we don't have a normal, we can of course create our normal. And if you recall, so if you do have 3 points, I can literally take, okay, and find 2 vectors that are going to be on this plane. And that is done by simply taking, let's say, 1 point and another point, and then going from 1 point to another, right? And then finding the difference in between. And these could be your vectors. So let's say 0, 1, 4, minus, and then this is going to be my other vector, which I turn the point into a vector. And so from here, so this is going to be one of them. So I guess this is going to be 1. 1 minus 2, so that's negative 1, and then 4 minus, so that's a plus, so that's going to be 5. So I have one vector. Now my second vector that I would have is, again, you can choose any 2 points, just don't choose the 2 same ones. So I can start off with the first point again, change it into a vector, do the subtraction, it's going to be 1, 1, 1, and that's going to give me my second vector. So within here, so this is going to be negative 1, I guess, and then 1 minus 1, so that's 0, and then 4 minus 1, which is going to be 3. We can just check and make sure that these 2 vectors that we have are non-collinear. These points were actually non-collinear, so we're not going to get collinear vectors. So now that that is true, we can certainly find our normal by using the cross product. So the cross product, so as you know, you can use your right-hand rule, so depending on how it points, right, from one to another. It doesn't matter which one you take. You can go from V1 crossed with V2 or V2 crossed with V1. So the direction, if it's up or if it's down or, sideways or this way, that doesn't matter. We just need a normal that is perpendicular to the plane. So in order to do that, I can take these 2 points, these 2 vectors, and indeed find the cross product. So let me just do the cross product. Here's our normal. So this would have been our normal from the cross product. So notice that we can indeed do the cross product. So now we have our normal. Now, we have plenty of points. We just need 1 point, but we have 3 points. So we can choose any of these points. And we can do exactly what we did in the previous example. So what we can say now is, okay, we can take our normal. So for instance, we can take -3, -8, -1 right there. Now you can, multiply this by, because I just see that there's negatives, you can multiply this by a scalar, so it doesn't change the normal. It will change, again, either it's going to be going up, down, whichever way. I'm going to multiply this by -1 just so that I don't have these negatives in here. And now I can take the dot product. And by the way, you can multiply by any scalar that you like, right? So if you take a normal and then you multiply it by a scalar, k, so some scalar, as long as it's not 0, then you still get your normal. It's just scaled, remember? So it can be scaled. So if you want to make your normal a unit vector, you can do that if you wanted to. If you don't want to have the negatives, which I don't, so I just multiplied it by -1, and I have a normal. All you want is, you want a scaled version. That's convenient for you. What you choose, again, is up to you, unless your teachers have some strict rules, that they want the first, leading kind of number or coefficient, okay, for the normal to be positive, so that could be indeed the case. But you can multiply it by anything you like. Now, the second thing that we will do is we're going to say x, okay, and then minus one of these points. I'm going to take, I like this one, all right, because it's 1, 1, 1. It's going to be easy to work with, so x. So I'm going to just stick in this. So I'm going to do the dot product to find our equation. And this is going to be 3x minus 3. It's going to be now plus 8y minus 8. And it's going to be plus z minus 1 equals to 0. So writing this out, 3x plus 8y plus z. And then I got to worry about this. So -3, -8, so that's -11. So it's -12 equals to 0. So there you have it. So now you have found your equation. It's in your standard or scalar form. You can use math3d.org if you wanted to. I've used that in the past to be able to graph it so that you can see this if you wanted to. You can plot the points, you can plot the plane, whatever it is that you like. But that's how you would actually find these. Now, that is the introduction of the dot product, and it ties in for you how it relates back to our standard equation of a plane in 3D. All right, so thanks for watching. Hopefully we'll see you in future videos. Okay, take care everybody. Happy studying. Bye.